So now we know what an imaginary unit is, a complex number, and also how to add, subtract, multiply and divide complex numbers. We're going to move now to looking at a graphical representation for complex numbers and a couple of new representations for them as well. And the new representations, polar and exponential form, will make it easier for us to multiply and divide complex numbers. So we already have the algebraic representation, the Cartesian or rectangular form, z equal to x plus iy. X is the real part and y is the imaginary part of our complex number. The graphical representation that we're going to introduce is going to map that number to a two-dimensional plane. Now the two dimensions are going to correspond directly with the imaginary component and the real component of the number. And we're going to call that representation the complex plane or an argand diagram. Both mean the same thing. In the complex plane, which looks a lot like the Cartesian plane, our coordinate xy is going to represent the number z equal to x plus iy. So what we're going to start to see is representations like this. Looks just like a Cartesian plane, except what we're going to have for axes is the real part of z and the imaginary part of z will be what we've got on our axes. Then we'll have coordinates like something like this, which we can say is z, and that's going to correspond with x along the real direction and y along the imaginary direction. So depending on what x and y are, will dictate where we find z in that complex plane. The graphical representation like this is going to allow us to define another representation for z, known as the polar form, and in an extension, the exponential form. To be able to write z in the polar form, what we need to do is introduce the concept of the modulus and the argument of the complex number. And these are basically going to translate to how far is it from here to my number, and what is this angle in here? That's going to tell us what the modulus and the argument are. See, they are in definition form. The modulus, which we write as this, z with bars around it, kind of looks like the absolute value of z, or the size of z if you like. The modulus of the complex number is the distance from the origin to the point z in the complex plane. Now jumping back, distance from the origin to the point z looks a lot like the hypotenuse of this right-angled triangle, which has a base x and a height y. So the length of that line should be, by Pythagoras' theorem, square root of x squared plus y squared. And that's exactly what we have as our rule for the modulus of z, or the definition of the modulus. It's always equal to the square root of the real part squared plus the imaginary part squared. The argument, on the other hand, theta sometimes, or sometimes you see it written as arg of z. That's the angle formed by the positive horizontal axis and the ray that joins z to the complex plane with the origin. So here, it's this little angle in here. If z was down here, I'd be talking about this angle. If I was over here, I'd be talking about this big angle, and if I was over here, talking about this angle back here. Sometimes we give values between 0 and 2 pi. I tend to give values between minus pi and positive pi, basically just because of the way I've drawn this picture here. But really, it depends. Different textbooks do it in different ways, and it doesn't really matter, as long as you're clear about which one you're using. So it's the angle formed by the positive horizontal axis and the ray that joins the origin to z. In other words, again using some trigonometry, theta is the angle which has a tan of y over x. So let's just have a look at this one for example. Tan of theta opposite y over adjacent x. So theta is that angle. Just going a little bit further, we actually introduce a special value of the argument, the principal value, and that's just the single value of theta in between minus pi and pi. Because remember, there's infinitely many angles that satisfy this equation by adding 2 pi to them. So the principal argument is the one that we would usually use when we write the modulus argument or polar form of the complex number. So you can write that polar form fairly succinctly, like this, where we've got modulus of z and theta, but that can get a little bit confusing if you're not sure which one you're using. Maybe it looks a little bit like z equal to x and y, the coordinate form. So because of that confusion, what we actually do is write the polar form in a different way. But before we get to that, we're going to see how we actually form that different way of writing it. So let's stop for a minute and think about, if I knew what the modulus and the argument were, how could I figure out what x and y are? So remember, we've got something like this, z sitting up there. So say I knew what that length was, and I knew what that angle was, but I didn't know what y was, and I didn't know what x was. Say I didn't know what those lengths were. Well, again, we can draw back on what we know about trigonometry using the modulus of z and the angle theta to figure out those unknown lengths. So thinking about this opposite side on the triangle here, remember that sine of theta is equal to the opposite side, y, over the hypotenuse. So that tells us that y is equal to the argument of z times the sine of theta. Okay, so we can regather the y value in our Cartesian form by using the modulus and the argument. That's exactly what I've written down here in this little rule box. You can do the same thing. Cos of theta is x over the modulus of z. Gives you that x is mod z times cos of theta. So in other words, if we know the modulus and the argument, we can figure out again what x and y are in the Cartesian form using right-angled triangles and Pythagoras and trigonometry. So this tells us what we can do to rewrite our polar form in a neater, little bit longer, but neater and less confusing way than this one up here. So here it is. Given a complex number z equal to x plus iy, which has a modulus mod z and an argument theta, we can write it in Cartesian form. That's the initial one that we first learnt about. Or we can write it in this form, which is the polar form. Okay, now how's that made up? Well, we've got modulus of z times cos theta. Remember from the previous slide, mod z cos theta is just I. Mod z times sine theta is just y. So if we just rewrite it in that form, we've got our new polar representation. Makes sense, still equal to the same thing, and not as confusing as this one we see up here in the yellow. So that's the polar form of z. Let's check it out in this example. I've got z equal to 1 minus I, and I want to find the modulus and the principal argument of that number, and hence write it in polar form. So remember, the modulus of z is equal to the square root of the real part, 1 squared, plus the imaginary part, which is minus 1 here, again squared. So we've got the square root of 1 plus 1, or square root of 2, or if you like, about 1.414. Now where does this number sit? If I graphically represent it, real, imaginary, got 1 on the real axis, down to minus 1 on the imaginary axis, so z sits down here. So the length of that dotted line is the square root of 2, and the angle we're looking for is this one right here. So let's see. Remember that tan theta is equal to y over x, or imaginary over real. That's minus 1 on 1. Now, some of you might know what the inverse tan of minus 1 is, or in other words, the angle theta which gives a tan of minus 1. You might also be able to figure it out here. We've got a right-angled triangle. Both sides are 1, so this is a 45-degree triangle. But if I wanted you to have a look at the calculator for a moment, I'm just going to jump over there. If I want to find the inverse tan of that, I need a 1, 1 minus, and then I want the inverse tan, and it tells me it's minus 45 degrees. So that tells me theta is minus 45 degrees, or if you like, minus pi on 4 radians. So that is one value for the argument. Just to check that it's actually the principal value, we need that to be between minus pi and positive pi. And minus pi and 4, of course, yes, it sits in between minus pi and positive pi, so that's fine. We've now got the modulus of z is root 2, the principal argument is minus pi on 4, and so now we can write that z is equal to, in polar form, the square root of 2 cos of minus pi on 4 plus I sine of minus pi on 4. So that's our polar form right there. Some of you may know of cis notation, root 2 cis minus pi on 4. It's just like a shorthand way of writing the same thing. You can do that if you like. I'm not a big fan of it, but it's just a shorthand way of writing the same thing. Let's just quickly have a look at going back the opposite way. This question asks us to rewrite a number written in polar form back in standard Cartesian form. So all I've got to do there is really just evaluate everything. So I've got 5 cos pi on 3 plus I sine pi on 3. I'm going to expand it out. Get 5 cos pi on 3 plus I times 5 sine of pi on 3. So jumping to my calculator, I want to do pi divided by 3, and then I want to make sure I'm in radians. Take the cosine of that, gives me 0.5, multiply by 5, and I get 2.5. And then I've got plus something times I, that's going to be sine of pi on 3, so I need, again, pi divided by 3, and then I want the sine of that, and then I want to multiply by 5. So about 4.33. So I've got 4.33i. If you want to use the exact values for sine pi on 3, that's quite okay, go ahead and do that, but the decimal is also fine for our purposes. So that's our standard Cartesian form for this number 5 cos pi on 3 plus I sine pi on 3. Just to finish this one off, I'll show you the last form that I'm really going to introduce. The polar form, writing it out in this long cos plus I sine thing, it's a bit cumbersome, it's a bit long to write. So there's this really great formula called Eulers' formula. Euler's formula says cos of theta plus I sine theta is exactly e to the I theta. It's really amazing, but anyway, it makes things really short to write. So we can actually use that to rewrite any complex number we like that we know has a modulus z and principal argument theta in this really short, succinct way. Mod z e to the theta I, or I theta. So we're going to use this a lot, this exponential form, just because it's so easy to work with, it's so short, and it lets us do multiplication and division really easily, and it also lets us solve equations much more easily than any of the other forms. So more of that as we move into the final videos for this section. But for now, you can check out section 3.2 of the text up to 66, or any other text that you like talking about the same sort of topic. There's a few exercises in the worksheet and in section 3.2 of the text, and as usual, write down your notes and questions.